The topic of today's lecture is period doubling cascade. Before going to this topic, let me remind you where we ended last time. So we were considering logistic map, un plus 1 equals to r un 1 minus un. So we have parameter r, which is positive but doesn't exceed 4. And u naught, initial value of our variable u, lies in the range between 0 and 1. So in this case, as we know, from here it follows that un also belongs to 0, 1 for any n. So what we know how our, so we have u equal to 0, 0, 1. So u1, which is equal to 0, which is stable when r is between 0 and 1, and it becomes unstable when r is more than 1. When it becomes unstable, we get second fixed point, which is u2. So this is 1, tends to 1 when r is increasing, and when r equals to 3, u2 becomes unstable. So what we know, at this point we know that it was a transcritical bifurcation. We discussed this before. And it is what we found on the last lecture. And it's called flip bifurcation because at this point, when r equals to 3, fixed point u2 becomes unstable, fixed point u1 is also unstable, and in fact what is observed in this dynamical system when r is slightly exceeds u3, so we have this kind of flipping behavior. Flipping dynamics is associated with two periodic solutions, and two periodic solutions, as we seen in the last lecture, is associated with fixed points of another map. So what we consider map un plus 2 equals to f2, to composite map, and fixed points of this map to periodic solutions. So this map, what I can do, if we say x n equals to u2n, then what we will have, if after this substitution we will have xn plus 1 equals to f2 xn. And we remember what is f2, where f2 is say of xn. Which is f of xn. So f is f for logistic map, it will be xn 1 minus xn, and it is whatever r squared xn 1 minus xn, and here 1 minus r xn 1 minus xn. Now, if we look at the plot of this function, it is a polynomial of fourth degree. It will look like this. Zero, one, and this is diagonal line. And now, so we have this it was our first solution, which was u naught. This was u1, this was u2. And when r is large enough, so this here is, then we will have something like this. So this will be extra two solutions, x3, x4. Oh, let's call them u. It's what we called u3, u4 before. So here r is less than 3, and here is r is more than 3. So if r is more than 3, we get extra pair of fixed points for xn plus 1 equal to f2 of xn, which are flipping, which are over period to solutions for un plus 1 equal to f of un. Now, if we look at bifurcation diagram for this map, xn plus 1 equal to f2 of xn, we will see following phenomenon. So this is r, parameter r, these are fixed points. So we have again one fixed point which is stable between 0 and 1 and unstable if r is more than 1. We have another fixed point, so this was u1, this was u2, which was stable and becomes unstable here, and we have here two extra fixed points, u3 and u4. You can see, well, you can check it at when r equals to 3. u3 equals to u4 and equals to u2. When r equals to 3, u2 equals to u3 equals to u4. So this is evident from the formula we derived last time. So again, so this one is transcritical bifurcation. But this one now, it is different. It's not flip, because here in flip it was different. We had u2 which became unstable. There were no U3 and U4 fixed points, but here we have, at one hand, U2 becomes unstable, and two new fixed points, U3 and U4, appear, and this is called pitchfork bifurcation. So what is transition? So okay, what characteristics of pitchfork transition between 1 and 3 fixed points and second, change in stability of 1, which is one fixed point, and 2 new, let's say new fixed points have the same stability. Opposite to that of 1. And now we are ready to talk about period doubling cascade. So what happens? What happens later on? Later on with two periodic solutions. At r equal to 3, two periodic solutions appear. Occur and stable. At r equal to 1 plus square root of 6, we checked this before, two periodic solution becomes unstable. We know this, we found it, but what we didn't find, and it's very hard to show, at r equal to 1 plus square root of 6, four periodic solution appears. And stable. Then when r is increasing, four periodic solution will eventually become unstable and 8 periodic occurs. So this can be illustrated on bifurcation diagram like this. R. So assume, so this is, let's say, R equal to 2. So this is U2 which is stable. It becomes unstable when r equals to 3. Then two periodic solution appears which is stable, and then it becomes unstable at roughly 3.45. Then when it becomes unstable, 4-periodic solution appears. Then it becomes unstable at certain value of our parameter, then 8-periodic appears, and so on and so forth. So all of this is called period doubling cascade. Period doubling cascades are observed in many maps. This is kind of very common feature of maps, and there are two universal constants associated with period doubling cascade, which are called first and second Feigenbaum constants. So first Feigenbaum constant is this. We know that at R1 equal to 3, 2-periodic solution appears. At R2 equal to 1 plus square root of 6, which is roughly 3.45, 4-periodic solution appears. And let's put it like this: at Rn, at this bifurcation value of parameter R, we 2 to the power of n periodic solution occurs. And we can put them like this. This is R. Let's say this is R1. This is R2. This is R3. This will be R4, and so on. So this in a limit sequence of R's, Ri's equal to 1, and so on, and so on, infinity, is converging to geometric progression. And there is a constant associated. It's like common factor for this geometric progression, Rn minus Rn minus 1. So this is, let's say, this distance divided by Rn plus 1 minus Rn. This is distance. So this tends to roughly 4.67 as n tends to infinity. So this is common factor for geometric progression. This is called first Feigenbaum constant. First Feigenbaum constant. And using this Feigenbaum constant, we can estimate when we will have infinite periodic solution. You see, we have R to the power of n. No, sorry. 2 to the power of n periodic solution when n tends to infinity becomes chaotic. Why it becomes chaotic? Because if periodicity is infinite, if periodicity is infinite, we can't predict behavior. Let's put it like this. Therefore, what we need, therefore we can find out at what value of r we will have chaotic dynamics. So this happens at r infinite. We will have at r infinite, we will have 2 to the power of an infinite periodic solution. And r infinite, we can put it like this. R infinite equals to r naught plus r1 minus r naught plus r2 minus r1 plus so on plus r n minus rn minus 1 and plus so on. So this equals to, we can put it, this is r naught plus r1 minus r naught. This is fine. And now we can use first Feigenbaum constant. So this means that r2 minus r1 is r2 minus r1 can be replaced by r1 minus r naught divided by delta, roughly. So this is, we can put it as roughly because it's not exact. And next would be r3 minus r2. This will be r1 minus r naught over delta squared. You remember this is roughly geometric progression and so on. Now this equals to r naught plus, now we can take r1 minus r naught outside of brackets. It's common factor, and what is left is 1 plus delta to the power of minus 1 plus delta to the power of minus 2 plus so on plus delta to the power of minus n plus so on. So this is geometric sequence. And this can be represented as r naught plus r1 minus r naught times 1, it is sum of geometric series, 1 minus delta to the power of minus 1. So, and now we know everything. Rho naught is 1. It is when we got U2 solution. R1 is 3. It's when we got 2 to the power of 1 solution. 2 to the power of 1 periodic solution. This is 2 to the power of 0 periodic solution. So what we got is 3 minus 1 times 1 over 1 minus delta was 4.67. So it is 4.67 to the power of minus 1. And this can be calculated. This is roughly 3.54. So what is our conclusion? At r roughly 3.54, we get chaotic dynamics.